Critical Scenes Philosophy by Professor Dacheng of University of Sydney, Australia. Professor Pinpul P. Chaudhary of Techno India University is going to chair the session. Professor Chaudhary is a Pro-Vice Chancellor of Techno India University and former Professor of Indian Statistical Institute. He was a J.C. Bose Fellow and INAE Distinguished Professor at Indian Statistical Institute. So I request Professor Chaudhary to please come on stage and chair the session for us.
Okay, good afternoon, everybody. It's nice that a Australian laureate fellow, Professor Dacheng was supposed to talk in this session. Unfortunately, he could not come, but he made a nice video of his talk and present here. Let me tell a little bit about Professor Chao. He is a professor of computer science and Peter Nicholas Russell here in the School of Computer Science, and then advisor and chief scientist of the Digital Sciences Institute, and the founding director of Sydney AI Center in the Faculty of Engineering at the University of Sydney. He has published papers in almost all the prestigious journals and conferences, and he received several Best Paper Awards. In addition, he received Australian Eureka Prize, IEEE ICBM Research Contribution Awards, and Computer Society McMurtry Technical Achievement Award. He is a fellow of Australian Academy of Science, Royal Societies of NSW, TWAS, AAAS, SCM, and ITP. It is our privilege to listen to this video, but we could not interact during the talk or at the end of the talk because of this. Maybe some mechanism can be done, maybe some emails can be sent to them if there is questions at the end. Maybe you people can take care of that. So,
thanks for the committee's kind invitation. I'm so pleased to introduce my recent research developments on foundation models. I realized a revolutionary technology changes everything. 10 years ago, we got AlexNet developed by Hinton's group to make a new yet immense success in the 2012 ImageNet Challenge. I believe at that time, all researchers in computation community were surprised. The next 5 years, we have witnessed an enormous change in computation because we have refreshed our understanding to almost every computation task by deploying convolutional neural networks. The layman's thought our success is only because of big data and high-performance GPU machines. However, we know the truth is the seamless integration of new algorithms with big data and GPU machines. The years between 2005 and 2018 were exciting, but the subsequent 3 years turned out to be boring. Transformer broke the recent silence and now is rewriting the history again. Now it's the time to embrace transformers and foundation models to train on broad data, which offer plenty of opportunities to revolutionize industries, education, entertainment, and even research. During this talk, I will emphasize the fundamental concept that more is different, and encourage us to expand our thinking beyond the Wittgenstein's philosophy, which states that the limit of my language is the limit of my word. Today's transformer, yesterday's AlexNet. We will first review the AlexNet moment in deep learning. AlexNet was born in 2012. Since then, computation researchers have devoted themselves to devise new network architectures, including resilient networks, to design fast training and inference algorithms, to deliver network compression gains, and to deploy results to check in practical utility and commercial variabilities. And for all the targets, we have a new opportunity to reconduct them based upon the new foundation models. History is always surprisingly simple. AlexNet had its moment of glory with its tremendous success in the 2005 image challenge. Well, resilient networks further added this convolutional architecture, leading to fascinating commotions. Transformers' outstanding performance on the blue benchmark inspired OpenAI to design ChatGPT, generating 100 million users within 2 months. Revolution is just around the corner. This transformer tree is stemmed from one vector and evolved into 3 series of factors. The include only first, the included decoder T5, and the decoder only G. Each has its specific advantage. First is effective in understanding tasks. T5 is more friendly to multimodal inputs, and the GPT change our understanding of generating tasks. Recently, there appeared a reasonable trend of unifying transformer-based architectures for both vision and language. This observation implies the possibility of an impending shift toward transformer for cross-model tasks. It's possible that such shift will lead to the development of large multimodal models that can operate aligned different modalities of data. Exemplified by GPT-4, which likely exhibits improved cross-modality abilities. Nonetheless, the remarkable success of ChatGPT has sparked concerns about the possibility of technological singularity. Last time we worried about this because of the success of AlphaGo in 2015. However, before the success of ChatGPT in early 2023, our understanding of AI primarily resolves around its challenges in practical deployment. Well, its ability to achieve recursive self-improvement remains far out of reach. AI driven by foundation models such as ChatGPT and GPT-4 can be different because of its recursive self-improvement capability. Although the capability is not strong, with the fast increase of computational power, we need to find ways to better understand AI and appropriately regulate its development and utilization. Well, ChatGPT and the large language models have impressive capabilities. They have certain limitations. First, they may struggle to accurately comprehend human instructions, especially when written in languages other than English. Then they provide contradictory answers for the same question presented in different languages, and fail to conduct a correct logic inference even for very simple questions. Hallucination is another serious problem. This refers to situations where they generate responses that sound plausible, but they actually false. There are so many other problems, most of which are relevant to human value alignment. Here I provide 4 examples. For example, this question, Jan given John candy because she was hungry. Jan was hungry. Are both sentences inhuman? GPT's answer is actually yes. The two sentences have an inhuman interpretation. The first sentence implies that Jan was hungry, and that this was the reason for giving candy to John. So the second sentence can be inferred from the first. This is called forward inference. It's absolutely wrong logic. However, for some people, they may not recognize this is wrong logic, but actually the logic itself is wrong. So I also have other examples. Given limited time, I'm not going to go through all the examples, but if you have interest, so you can read them after the presentation. However, there are ongoing efforts to improve their capabilities. The development of foundation models has been rapid, paving the way for the further advancements. Related technologies such as reinforcement learning with human feedback or RFHF are helping to achieve human value alignment, improving the ethics and social value alignment of IT habits. With various extensions, ChatGPT is consistently improving and evolving. For example, with broader integration, ChatGPT can access and analyze the latest information and news. The integration of math tools like calculators can enhance ChatGPT's math capabilities. Rome wasn't built in a day. The whole journey commenced from the 2015 attention model. The transformer model developed by Google in 2017 led the whole community to believe that attention is all you need. In 2018, OpenAI devised the generative pre-trained transformer or GPT by using unsupervised retraining and supervised fine-tuning to improve language understanding. So almost 5 years, OpenAI achieved this revolution and is changing the industry form. We have to remember, even around the late 2022, just last year, a considerable number of media outlets openly criticized the training of foundation models, arguing that it not only pollutes the environment and consumes resources, but also fails to bring any tangible value. There are 3 transformer-based architectures. They are OpenAI's decoder-only GPT, Google's encoder-only BERT, and the encoder-decoder T5, as I mentioned before. Well, I guess everyone is surprised by ChatGPT and would like to find appropriate ways to embrace GPT-based language models. Why is GPT? GPT shows several advantages. First, they have strong text generation ability, making it particularly suitable for natural language generation tasks. Second, they are capable of few-shot and zero-shot learning, allowing them to quickly adapt to new tasks with limited training data. And third, they are highly efficient in terms of training. This is so important because we know the current models are very large, and then need to go through a very large repository of training data. Recently, there have been rumors suggesting that OpenAI's success is merely a coincidence driven by luck and not reproducible. However, the reality is that they actually conducted extensive scientific experiments systematically summarize the paths to success. It is through these efforts that OpenAI has achieved its current accomplishment. This is a fascinating paper, Scale Laws for Natural Language Models. It suggests that exponential growth in any of the three elements, computing power, data scale, and parameter scale, can lead to a linear growth in model performance. Especially as the size of the language model increases, they become better equipped with handle an increasingly diverse range of natural language processing tasks, enabling us to build more sophisticated and versatile natural language processing systems. And we can see, once we have more and more parameters, our models are capable to all tasks. This is very important. At that time, the larger the model will be able to manage the word knowledge. The scheme law has laid the foundation for OpenAI's steadfast focus on large language models, demonstrating that scaling can be a reliable path to improve model performance. This underscores the idea that positive changes can lead to positive changes. The idea of models different is a title of a popular article published in Science in 1972 by Folkward Allison, the winner of the 1977 Nobel Prize in Physics. In this article, Philip discussed a range of topics from the study of elementary particles to the study of condensed matter physics. He pointed out that as the number of research subjects increases, quantitative change can lead to qualitative change. From Philip's observation, we can expect that by embracing this mindset, most different foundation models can bring us to the era of artificial general intelligence or AGI. The idea of models different as a well-known phenomenon called emergent ability of large language models. The ability that the large language models outperform small models significantly on complex tasks. However, the recent research from Stanford has questioned this phenomenon, suggesting that the emergent capabilities may be artificially created by selecting the evaluation metrics. Nowadays, if we closely examine these metrics, they represent a reasonable method for evaluating highly difficult tasks. On the contrary, this further illustrates the advantages that large language models have over smaller ones in solving complex problems. So, this paper, to some extent, demonstrates that large language models has the emergent foundation model training is costly. Shall we really put a serious effort and resource in such expensive boundaries? We need rigorous guidance from theoretical investigations. Although current deep learning theory is still in its infancy, we can already proceed to research long-term goals for editorial control. Second, the high processing ability in information theory. We find that under the premise of a sufficiently small training error, the generalization error of the network will exponentially converge to zero, and the number of network layers with information decay properties decreases. So basically, we can use a Markov model to describe a deep network. And so the mutual information between input and output is not increasing as it goes through the network near area. This suggests that the hierarchical structure in a deep network is very essential to filter out redundant information which is not useful for classification. The feature mapping for each layer in deep network is likely to be non-important, which results in information loss according to the data processing equity. So why are we so confident that they're not inverted? Because they are convolutional operators, pooling layers, redo activations, and dropout operators. We know this is provable that all these operators or layers are actually not inverted. To a certain extent, this finally explains why we need deep networks. Of course, we still have to obey the principle of outcomes reason and avoid unnecessarily multiplying entities. So this means when we train this network, we still need to use a sufficiently large training set. On the other hand, the research on neural network ways represented by the neural content kernel of that the initialization of an infinitely wide neural network is equivalent to a Gaussian process. It also indicates that the training process of the neural networks can be described as a kernel method, which can guide the network to find the most optimal solution. In this study, neural content kernel described the local dynamics of a sufficiently wide neural network, and the theory states that a sufficiently wide network has fewer local optimal solutions. Additionally, according to statistical learning theory, the generalizability of a model is guaranteed given a sufficiently large training sample. We know that neural networks are very sensitive to initialization parameters, especially small-scale networks. Our theoretical analysis shows that large networks trained on broad data are insensitive to initialization parameters, and the corresponding generalization algorithm is determined by the training sample size. Moreover, the theory of neural content kernel suggests that a sufficiently wide network will effectively avoid local poor solutions. Therefore, training mechanisms such as training plus fine-tuning have high efficiency and good adaptability. In this mechanism, a large model is trained on a large model training sample, and then fine-tuned on a small amount of downstream data to achieve very good generalizability on downstream tasks. The large model trained on massive data provides a very good initialization for fine-tuning the model on downstream tasks, enabling the model to converge on downstream tasks quicker. Multimodal learning has recently received intensive attention, especially since the success of DALI-2. Our theoretical analysis in the past point out that through multimodal learning, we can effectively improve the stability and generalizability of the model. This is mainly because multi-view or multimodality data have not only consistent information, but also complementary information, which will help us learn the latent in-text space. We show theoretically that by combining multiple views or modalities, we can obtain abundant information for latent in-text space recovery. Moreover, we show that the complementary between multiple views or modalities is beneficial for the stability and the generalizability. This very recent success of GPT-4 empirically verifies our theoretical findings by showing that visual modality improves GPT-4 on challenging language tasks such as GRE, quantitative, and verbal tests. In addition to the recent focus on multimodality, multitask learning has once again caught our attention. Google Pathway Framework provides a glimpse into the bright future ahead for large model-based multitask learning. Why does multitask learning play an important role in the era of foundation models? It can improve model accuracy, memory efficiency, and inference speed. When compared to training tasks individually, therefore, multitask combined with deep learning has been widely used for many computation natural language processing tasks. This inequality shows that by increasing the task number and the assumption that the future structures similar, the algorithms will be more stable and generalizing better. Deep learning has become an important means of achieving AI with its complexity and variety, guiding us towards the development of foundation models. There are many reasons behind this development and trend. Our recent book, Foundation Deep Learning, covers the theoretical foundation. I hope that we can complete the work within this year, or this is actually far behind our original strategy. After here, I believe you have started to more or less believe that foundation models will drive the future. However, the recent leak with Google memory has sparked widespread discussions. It seems all AI companies are attempting artificial general intelligence by foundation models. Well, data and computational power are necessary for training AGI. Algorithms remain the true core. And we must not overlook the value of algorithms because excellent algorithms can efficiently leverage data and computation power. There are so many dimensions where algorithms can make a difference. Given limited time, I want to talk a bit about architecture design and model training. With the foundation models trained on board data, we can easily deal with the various downstream tasks. The key is to equip foundation models with the word knowledge. The definition of a foundation model to target tasks is similar to developing application programs based on an operating system during the PPA era. The operating system corresponds to the foundation model, and the process of developing application programs corresponds to adapting pre-trained models to target tasks. However, it is challenging to train foundation models effectively and efficiently. Here, I introduced a small piece of work on large scale for training discriminative language models. Although generative language models are popular, discriminative models are more effective on understanding tasks. Discriminative language models are basically based on master language modeling objective, which involves a random masking strategy to mask some tokens, and then enforce the models to learn to recover word information from the masked tokens. Such a random masking process is usually criticized as being suboptimal, as it allocates an equal masking rate for all tokens. In particular, the masked tokens are sometimes too easy to guess with only local cues or shadow patterns. While the informative tokens can carry more critical linguistic knowledge may not be selected. So here I show some examples. Different mask tokens refers to different levels of difficulty in model to train. Choosing appropriate content for masking can improve the data efficiency of model to train. That is, how to design an effective masking strategy is one of the key issues. There are many studies that attempt to improve master language model by exploring a diverse and linguistically motivated masking strategies, such as span level masking and entity level masking, and PMI-based masking, to fully leverage the pre-trained data. Specifically, instead of masking individual tokens, span level masking strategy randomly selects starting point of a span and then samples a span size from a geometric distribution and masks the selected span. By doing so, masking spans instead of single words can prevent the model from predicting masked words by only looking at local cues. For entity level masking, a span containing named entities will be masked and it can explicitly integrate prior knowledge regarding the entities into the routine process. This PMI-based marketing strategy uses point-wise neutral information to identify a set of contiguous engrams that exhibit a high co-occurrence probability relative to the individual occurrence probability of their components. By masking these meaningful steps, the models are enforced to predict them using the context information, but not relying on the local cues. Although achieving remarkable performance, these strategies actually still have many limitations. First, their implementations are relatively complex, as they usually require annotation derived from external models of tourism to select tokens for masking. For example, the entity level masking relies on the off-the-shelf named entity recognition tools to identify the entities. Second, in order to ensure the effectiveness of masking strategy, most previous works train the language models from scratch without reusing the existing trained language models trained with the vanilla masked language model. So we know this is wasteful and inefficient and not so friendly to downstream tasks, because for downstream tasks we don't have much data. To address these problems, we devise an effective self-evolution learning mechanism. Instead of training a trained language model from scratch based on carefully designed and complex masking strategy, our mechanism aims to strengthen the pre-trained language model's capability and data efficiency by continuously learning from the informative yet underexplored tokens, which are determined by the existing pre-trained language model itself. So basically, the self-evolution learning contains two stages: self-questioning and self-evolution learning. In the first stage, the pre-trained language model is forced to locate the informative but underexplored tokens from the pre-trained data. We refer to those hard-to-learn tokens that are not learned well by pre-trained language models as the informative but underexplored tokens. After locating these hard-to-learn tokens, we then encourage the pre-trained language model to learn from them in the second stage, where we basically follow the vanilla masked language model to mask these tokens and then optimize the pre-trained language model by minimizing the loss between the predictions and one-hot figures. It should be noted that due to the hard-learned properties, directly enforcing the pre-trained language model to fit to the hard labels may lead to overfitting or overconfidence problems. Thus, before the proposal, token-specific label smoothing strategy, which considers both the precise hard label and the easily digestible distribution that is adaptively generated by the pre-trained language model itself. To investigate the effectiveness of our method, we conduct intensive experiments on various understanding tasks, including a diversity of masks from glue and superglue benchmarks, which are two of the most popular natural language processing benchmarks. We have two observations. First, self-evolution learning brings consistent gains for a wide range of understanding tasks in glue and superglue benchmarks, which verifies the effectiveness of encouraging the pre-trained language model to further learn from the information yet underexplored tokens. Second, self-evolution learning brings consistent and significant performance improvements among all pre-trained language models, proving its effectiveness and universality. We then conduct experiments on knowledge-intense tasks, such as RAD, SWAG, and Llama. We find that with the help of our self-evolution learning method, PRM achieves consistent performance gains on knowledge-intense tasks and can make a more reasonable and correct prediction on closed tasks. We can basically conclude that self-evolution learning can enhance the ability of the knowledge learning by further learning the semantic knowledge from this informative but under-useful focus. Owing to the new token level label smoothing method, we empirically find that self-evolution learning method can bring better model generalization. Specifically, we measure the generalization properties and realize the generalization of models with the training loss landscape. As we can see from the figures, the self-evolution learning boosts the performance of pre-trained models on auto distribution data and smooth the loss landscape and improve the generalizability of trained language models effectively. This new masking scheme can be deployed to improve different pre-trained language models. We have V2 champion the superglue benchmark, where this masking scheme contributed significantly. In this challenge, we support the top international organizations such as Google, Microsoft, Facebook, and OpenAI. In addition to natural language processing, architecture design is also critical in computation. Vision transformers have emerged as a highly promising approach to addressing various vision tasks. However, when dealing with the common high-resolution images, a significant challenge arises due to the large number of tokens involved in the transformer architecture. The comparative complexity of self-attention over the input token length exaggerates this challenge. To mitigate this issue, attention calculation within Windows has been proposed, which helps eliminate the computational burden. Nonetheless, the data-agnostic design of window-based attention restricts the flexibility of transformers in adapting to objects with diverse size, shape, and orientations. The limitation is illustrated in this figure, where multiple layers are required to capture the entire shape of the dog's head. Consequently, a natural question arises: can we transform the handcrafted windows into the linear ones, enabling the model to gather information from a wider range of the windows, just like the windows shows here? The window attention largely saves the computational cost. It divides the entire visual map into several non-overlapping windows based on predefined window size such as 7x7 or 14x14. Within each individual window, attention calculations are performed, constraining the attention mechanism to operate solely within that window. To promote a cross-window information exchange, a window shaping strategy is commonly employed in conjunction with vanilla window attention. This strategy facilitates the movement of windows across the visual map and thus enables cross-window information exchange. By transforming the full attention mechanism into local window attention, the computational complexity is significantly reduced. However, the fixed and the non-learnable window design inherently limits the learning capability of the model. How can we do that? To overcome this limitation, we utilize quadrangle attention. This approach focuses on more versatile window representation through parameterization techniques and leverages data-driven learning to adapt to quadrangle configurations. Quadrangle attention utilizes default windows to initially partition the input images. Subsequently, an end-to-end learnable algorithm is employed to predict the optimal target quadrangles for each window. By adopting this methodology, the windows within the model can learn to have diverse shapes and sizes, enabling them to effectively cover crucial areas for context. Consequently, the need for shifted window operations can be eliminated, and adaptive quadrangle configurations already encompass the necessary information, and they encourage effectively for information sharing between windows. That's the key. From a technical standpoint, we employ projective transformation from windows to quadrangles as a means of enabling the parameterization process. The projective transformation denoted as T is represented by a transformation matrix comprising 8 parameters. Within this matrix, the variable A defines the transformation of scaling, rotation, and shearing. Additionally, B represents the translation, or C is a projection vector. During our experiments, we discovered that directly regressing these 8 parameters of the projection matrix proved to be challenging. As a result, we chose to disentangle the projective transformation into several individual basic transformations and predict the parameters for each of these transformations separately. This also increases the explainability and all. The basic transformations including scale, the scaling transformation, the shearing, rotation, translation, and projection. By employing this approach, we're able to obtain the target quadrangle representation directly from the original window presentations. This is achieved by multiplying the transformation matrices corresponding to the predicted parameters for each basic transformation. Now let's examine the overall model architecture design. We have successfully integrated the quadrangle attention into 2 variants of variant transformers. This is the plane architecture, and also this hierarchical architecture. We compare the performance of swing and our Q-former, that is a quadrangle attention-based transformer, we call it Q-former. So under different settings, and one that Q-former will consistently outperform swing transformer. The performance gains highlight the effectiveness of the quadrangle attention in enhancing classification capabilities and suggesting its potential. We conduct an evaluation started by analyzing the impact of each basic transformation within the quadrangle attention. Q-former is capable to various vision tasks, including object detection, semantic segmentation, and semantic estimation. So the table showcases the result obtained, revealing that the Q-former consistently outperforms other models by a significant margin across different tasks. Importantly, despite its superior performance, it's worth noting that quadrangle attention introduces only a few additional learnable parameters and has minimal impacts on memory footprints. This characteristic demonstrates the advantage of quadrangle attention in terms of both performance and training cost. We realize the vanilla windows and learn the quadrangle windows in red. The first column here is the vanilla window used in Spain, while the remaining columns shows the quadrangles learned from Q-former. By examining these realizations, we observe that the quadrangles produced by quadrangle attention offer a more diverse coverage of regions within target objects. Quadrangle attention learns to dynamically adjust attention regions expanding the window size and capturing a more comprehensive context of the animal heads. Furthermore, the quadrangles generated by quadrangle attention exhibit variations in terms of size, location, and shape, featuring to different parts of the target. This flexibility allows for the capture of rich contextual information, resulting enhance the object feature representation. Here I show some videos that we apply this Q-former to impose localization. It was for a single person, for 2 people, and for a group of people. And from these videos, we find that the Q-former based post tracking, so the performance very robust and can achieve practically useful results. We also apply the Q-former to animal pose estimation. So we find that this Q-former performs very robustly on localizing all the key points of these animals. So for livestock analyzing, so I believe such kind of tools can be very useful. Here I present the visualization of the text storing results, a task that involves automatic design, automatic detection, and recognition of text images. And we find that the Q-former delivers very satisfactory performance. Foundation models consist of a huge number of parameters and need to accept raw data, and so the training is challenging. Now, decentralized optimization or decentralized learning plays a key role, because this paradigm is capable to deal with the concerns such as privacy, security, and scalability. In federated learning, data is distributed across multiple nodes, and computation is performed locally on the nodes, with only the model updates being transmitted to a central server. This approach helps to elevate the privacy and scalability concerns, but the central server is a bottleneck for efficient training, and is a potential security risk. In contrast, decentralized training moves one step further by removing the center server, allowing nodes to communicate and coordinate with each other directly. This approach offers a much better privacy, security, and scalability. In addition to distributed setting, the goal is to jointly optimize the common objective using multiple machines to achieve acceleration. This is typically achieved by partitioning the data across the machines and performing computation locally on each machine, with theoretical communication and synchronization to ensure that the models remain consistent. The traditional centralization server-based training method can be written in this form. In the case of synchronized and without local sets, this training method is equivalent to the classical SGD, also has the gradient descent. In training paradigms that rely on a single server, such as federated learning, the amount of communication required is directly proportional to the total number of nodes involved in the training process. This means that as the number of nodes increases, the amount of communication required to transmit data to the center server also increases. Therefore, it is important to carefully consider the design of the communication protocol and the distribution of computational resources in such training paradigms. It has been observed that the original data can be reconstructed from the gradient information transmitted to the central node in centralized learning paradigms based on a central server. This implies that there are certain privacy and security risks associated with such training paradigms. If the transmitted data contains sensitive or confidential information, it may be compromised, leading to potential breach in privacy and security. Considering these challenges, it might be beneficial to explore alternative training paradigms such as decentralized learning. These alternatives provide compelling advantages, including enhanced communication efficiency and fortified privacy and security assurances. Decentralized stochastic gradient descent emerged as a straightforward confluence of decentralization and gradient-based optimization. Unlike traditional methods, the decentralized stochastic gradient descent enables simultaneous model training across a multitude of workers, eliminating the need for a central server. Instead, each worker communicates solely within its directly connected neighbors through a communication matrix. To better illustrate this concept, here I show you several commonly used communication topologies in decentralized stochastic gradient design. For example, the ring structure, the grid structure, and the exponential structure. They are clear that this one is the most this one is much denser than the ring and the grid. The unique peer-to-peer approach shows that the decentralized stochastic gradient descent is this key advantage of localizing exchange, thereby optimizing bandwidth use, mitigating privacy breaches, and fortifying the network's security. In 2017, Lem proved that the convergence rate of decentralized stochastic gradient descent can be asymptotically consistent with that of stochastic gradient descent. And the denser topology can be beneficial to the convergence speed. However, our preliminary empirical studies stood on maybe kind of opposite position. Specifically, this curve reveals that in scenarios with a larger batch sizes, where the topological structures of decentralized algorithm can surprisingly outperform the centralized algorithm in terms of validation accuracy. This suggests sparser connections can be even better. Why? This is under-explained the phenomenon hints a non-neglectable gap between existing theories and the decentralized learning experiments. Drawing upon recent insights regarding the correlation between flatness and generalization, we assume that decentralized learning is actually performing sharpness-aware minimization. We show that decentralized learning conducts a region optimization as opposed to only optimizing individual points. This approach enables decentralized learning to converge to local minimum with a higher flatness, which are known to generalize better and be less prone to overfitting. By exploring the region around each point, decentralized learning is able to identify and converge to minimum that are more stable and robust. As they do not rely on small perturbations in the data, this makes decentralized learning a powerful candidate for training foundation models. The regularization effect in decentralized learning is dynamic and adapts to the convergence situation of the algorithm. During the early stages of training, the regularization effect is strong, which helps to prevent overfitting and ensures that the model generalizes well to unseen data. As the training progresses and the local models of the loss function become more consistent, the regularization effect gradually weakens. In the new era of AI, we exploring how to train large-scale foundation models like GPT-4 over a geo-distributed network with slow interconnections. This goal is driven by the untapped potential of millions of GPUs, often underutilized in personal computers across the globe. We are standing before a remarkable opportunity to harness this distributed computational authority to meet the increasing demand of large-scale model training. However, this approach presents significant challenges. Training such potential models in a highly diverse environment characterized by slow interconnections, we need to confront the unique issues. We face the variable network latencies, fluctuating bandwidths, and other constraints inherent in these expensive distributed networks. Either training from scratch or continue training is expensive and needs expensive data. The high cost for both computation and data operation poses a challenge for most businesses and the university labs. So in the era of foundational models, how can we avoid getting left behind and make the most of available resources to continue our research? In this constraint, we propose the learning to learn without data by appropriately reusing pre-trained models or solving downstream tasks. The goal of data-free meta-learning is to learn usable prior knowledge from a collection of pre-trained models without accepting their training data. To this end, there are two possible ways. The first focuses on meta-learning from white box models, which requires knowing the architectures and parameters of the pre-trained model. The second focuses on learning from a collection of black box APIs with only inference access to enable efficient learning of new tasks without data privacy leakage. So I believe that you can understand that this technique is more practical but more challenging. Recently, the concept of model as a service comes to reality without the access to the underlying models. Users only have inference access to the corresponding APIs provided by service providers like OpenAI or Google. For example, Motivation API of Google provides thousands of APIs for solving various specific classification problems. ChatGPT of OpenAI provides a conversational way to the users. It's also very clear that learning from black box APIs is much more challenging than learning from white box models because we cannot accept the architectures and parameters between the models in black box learning. Moreover, learning from black box APIs is not practical. Thus, below I only mentioned something about learning from black box APIs. Since we could only access the pre-trained models via private APIs with many challenges, the first is with only APIs, what kind of information can we have? The second, can we inverse the pseudo task by just querying these APIs? Third is how to deal with the black box API, pre-trained on different datasets with heterogeneous architecture inside. The first is how to map them with the rich rating from software prediction with the APIs. And the fifth is how to measure them under the setting of limited API parties. There are also three possible scenarios. The first one is API access. All APIs are designed for solving tasks from the single meta training subset with the same architecture inside. The second one is the API asset. All APIs are designed for solving tasks from the same meta training subset, but with heterogeneous architectures inside. The third one is also the most practical one, but also most challenging. That all APIs are designed for solving tasks from multiple meta training subsets with heterogeneous architecture inside. The pipeline for learning from black box APIs consists of two steps. First, for each API, we recover the training data starting from the random noise AI. By doing API AI, we gradually update the noise to label conditional data. Second, we split the recovered data into support set and the query set to perform meta learning with or by level methodology distillation structure. We first perform task recovery through the API inversion. For API AI, we recover the task of the training data AI and use it to learn the meta model. As shown in the figure, it consists of four components: a generator, an API AI, a gradient estimator, and a memory bank. The generator G takes the Gaussian norm Z as input and outputs the recovered data X. Because we have no access to the model parameters inside the API, we adopt a zeroth order optimization to approximate the gradient by just doing the API. We then propose a bilateral meta-knowledge distillation structure to perform meta-learning by transferring general meta-knowledge from a collection of black box APIs into one single meta-model with the recovered data. Our bilateral structure controls the knowledge flow from each API to the meta-model, where an intermediate task-specific model, which informs the general meta-knowledge to facilitate the visualization of task-specific knowledge. Through this bilateral structure, we can control the knowledge flow from the APIs to the meta-model, which encourages the exploration of more general meta-knowledge beneficial to the meta-model. We conducted experiments in 3 real-world black box scenarios, including API SS, API SH, and API MH. So I mentioned the settings before, so I don't explain that again here. The results in these 3 tables demonstrate the efficacy of our proposed approaches. Our framework achieves significant performance gains in a range of 8% to more than 21%. Given these empirical studies, so we conduct further experiments and application studies, and we have 2 observations. The first, it is feasible to meta-learn from APIs by recovering a pseudo tasks with only query access. Our method applies to APIs for training on different datasets with the arbitrary architecture inside. Second observation is we propose this bilateral data-free methodology distillation with a task memory replay to transfer general methodology from a collection of APIs to one single model, even under under settings of limited API parties. Ludwig Wittgenstein is a well-known Austrian philosopher. However, should we really adhere to his philosophical idea that the limit of language is the limit of the word? One picture is more than 1,000 words. And we know our limited language capabilities are insufficient to present our unlimited imagination capabilities. Therefore, we need to seriously consider developing AIGC, where AIGC means artificial generated content. So one promising direction is generating images from text descriptions. All these example images were generated by a foundation model trained in my group. Here, I'm really interested in some fascinating algorithm content generation. The current practical applications have demonstrated that if the content generation relies solely on text, it's difficult to control the outcome in terms of layout, object relationships, and details. Researchers have been attempting to control the output by utilizing different conditional signals. For instance, generating images based on object layout. However, this field faces numerous challenges, including structural errors and semantic inconsistency. With the technological advancements made over the last couple of years and our continued exploration into generative AI, we designed a focal attention and architecture based on the autoregressive former model. This approach has greatly improved the task of converting layouts into complex image generations. Under identical conditions, it generates all reasonable, effective, and realistic image content. Focal attention leverages the strengths of the autoregressive transformer model, applying attention mechanism to better capture the layouts and the details of the generated scenes. This mechanism allows the model to focus on critical areas of the input, thus providing a better translation layout into complex image scenes. Taking one step further, we can enable users to use multiple modality inputs to control the generating process. For common elements of different granularities, users can choose the various distinctive and control methods according to their needs and preferences. During multi-model control generation, our model takes into consideration the semantic contained within each mode of input, thereby generating content results that are more controllable and align better with user needs. To achieve this, we devise a model structure that supports multi-model input. Additionally, we propose a multi-model balance of function to address competition issues that may arise during the multi-model. Can we generate and edit 3D objects? In this regard, we designed a two-stream diffusion framework to facilitate the creation of 3D objects with control. Here, I provide you some experimental results. This result shows that we can generate images of different car models from multiple viewpoints. Furthermore, we can effortlessly edit the generated vehicles. Here I can show you some video demos or editing capabilities further demonstrate the flexibility and control our model offers. We can easily alter specific attributes of the generated vehicles, such as color, size, design elements, where maintaining the consistency and the realism of the object. This also demonstrates more potential for customizability, offering a significant advantage in various applications. So let's watch the video. And also this one for specific components and for the shape of the car. And also including the wheels can be adjusted according to the change of the shape. Here, I'd like to conclude my speech. In the past 10 years, deep learning has fully demonstrated its value in development of human civilization. This is success in attachment to the deep integration of data, computing power, algorithms, and the realization of vertical applications. With the rapid increase and the development of data, computing power, and algorithms, the concept of model is different. It illustrates the critical role of foundation models in breaking through the bottleneck in AI development. I believe foundation models have the potential to elevate AI from quantitative change to a qualitative change. On this journey, we are facing many technical challenges. We need to, for example, we need to design more advanced architectures that have better representation ability and more friendly to decentralized optimization, and may replace the transformer. Why should we believe that transformer is the most optimal architecture? Do we have some better architecture? The second, we need to develop a trustworthy AI to ensure efficiency, more robust, explainable, privacy, and fair. Third, we needed to devise the efficient optimization techniques for faster and better convergence, and also for the inference stage. And fourth, we need to achieve green AI techniques to reduce the carbon footprint of AI models. These challenges also bring us a lot of opportunities. Thank you.